Now we're going to cover the reactions for alkynes. Um, they're very similar to alkenes, but with some different reagents. So most of the reactions we're going to deal with are going to be addition reactions, as I said, just like alkenes. So they're addition reactions. The only thing is because alkynes have 2 degrees of unsaturation, they will react with 2 moles of anything. Okay, alkenes reacted with 1 mole of anything. Alkynes react with 2 moles. Okay, and some of the reagents are going to be different. They're not all the same, but some of them are similar. But some are going to be different. Okay. Now, one of the things I would like you to look at, if you can, is that alkynes are a little bit more oxidized than alkenes. Okay, so let me show you what I mean by this. Here is an alkyne. Here is an alkene. Alkene has more hydrogens on it, right? So because it's got more hydrogens, it's more reduced, which means this is more oxidized. Okay, so because alkynes are more oxidized than alkenes, they react a little bit different, okay, with some of the reagents. And if it helps you to understand that, it's good. If it doesn't help you right now, that's okay also. All right, it's not such a big deal, but for me it's very helpful to know, because then I can predict some of the products, okay, in there. But anyhow, let's go on, and then I will tell you which products are going to be different, for alkynes as being more oxidized than alkenes. But in any case, first of all, we're going to cover through all the addition reactions that we did with alkenes also, which is hydrohalogenation, halogenation, hydration, and then hydrogenation. So we have all these reactions to cover, and then we will also talk about oxidative cleavage that we had with alkenes as well. And then there are these 2 other reactions, which is very pertinent to only alkynes. Okay, they don't refer to alkenes at all, so there's no correlation there. Now let me see what else I want to manage over here. Yeah, I didn't give you a chart for these reactions because alkynes are a little bit different in their reagents, and also whether you have an internal alkyne versus a terminal alkyne, you can get different products. So that chart is going to become pretty useless for me, at least. I mean, I can make it for you, and actually I do. If you look on the website, I've given you all the reactions on one chart, so you can look that up. But I didn't make a chart here. Okay, it'll be yeah, we don't need it. Okay, so first of all, addition of hydrogen halide, okay, to it. So HX, X is the halogen, again, no fluorine, no iodine, bromine and chlorine only, okay, for now. So here what we are doing is adding HBr, or we are adding HCl. So when you add these, you only do Markovnikov addition. So hydrogen goes to the carbon with more hydrogen. Now, can you get something in the middle? Okay, so I've given this to you in 2 reactions, right? So I've given 2 steps over here. So if you add 1 mole of HBr, you end up getting this product, which is an alkene with a Br. And then with another mole of HBr, then you end up getting this kind of a dihalide. And the 2 hydrogens are, of course, over here on the terminal carbon, which is an imbalance, right? Okay, so generally, you cannot isolate this unless you really want to. So this is not a good way of making it. Generally, when you do these reactions, you want to go all the way through, okay, to the completely saturated alkyl halide. All right, that's what you want to do. So isolating it in the middle is a little bit different. Then the other thing I want to mention here is look at the 2 bromides. This, if you remember from what we talked about before, these are geminal halides because their bromines are on the same carbon. Okay, so not geminal halides. Okay, and the other thing is that if you had an internal alkyne, and I will write that reaction on the PowerPoint, is that if you have something like this, then if you add HBr, then just make sure, and again it's going to be 2 moles of HBr, so then you will still have something like this. Okay, now it's internal, that's all, but the hydrogens will go on the same carbon, so you'll still get geminal. All right, that's what I wanted to specify here. I think that's all I have. So the other thing, the last thing, absolutely last thing that I want to mention about this is, see, you're adding 2 moles of HBr in order for you to get to the alkane part here, alkyl halide or dihalide that you will get, because you're not isolating the alkene here. Okay, addition of halogen, again, you're going to be adding 2 moles of bromine here, and now there's, since there's nothing like hydrogen there, it doesn't matter whether I took a terminal alkyne or internal alkyne. All the bromines are going to the carbon that has the triple bond. Okay, so geminal, vicinal, whatever, it doesn't even matter anymore. Okay, so you're just saturating it with bromine now, or chlorine, okay, whatever it might be. Okay, so hydration for the alkynes is a little bit different because we're not using the same reagents as we used for alkenes. Alkenes we used acidic water, our acid hydrolysis, and then oxymercuration, hydroboration. We still have hydroboration here, but we don't use the first two. They're not strong enough, okay, to do the hydration. So for hydration we have 2 reagents that we use here. One is the mercury sulfate, and the mercury sulfate is similar to what we used before as in mercury diacetate, but mercury diacetate we don't use here. It's not strong enough to do the hydration, so don't use it. For alkynes, use only mercury sulfate in presence of sulfuric acid. And then the other reagent is the hydroboration reagent that we have used before. Now, if you remember from what we did with alkenes also, and I'm making this connection for you so that you don't have to remember too many things, you can easily connect the reagents. For mercury, even for alkenes, you got Markovnikov, and for hydroboration, it was anti-Markovnikov. It's the same thing here, okay? So if you have a terminal alkyne in which there is an imbalance for hydrogen, if you use mercury sulfate, then you get an internal functional group. Okay, so Markovnikov meaning that the hydrogens are going to the carbons with more hydrogen. If you use hydroboration, then you end up getting an aldehyde, okay, which is going to the carbon with more hydrogen. So it's anti-Markovnikov. Okay, so I've written that here for you because those are the key things about these two oxidations, hydrations, okay, that we're talking about. So be careful with that. Remember that. Now there might be some other reagents that you can find for hydroboration, and that's okay. That's not a problem, but only use the one that we use in our textbook. Don't use any weird ones, okay, because I will not give you credit for any reagents that are not covered in the textbook, okay, that we are using. Okay, so then if you had an internal alkyne, this was for a terminal alkyne. If you had an internal alkyne, then you will only get a ketone, because internal alkyne, both the carbons are exactly the same, so you will end up getting a ketone. Now, will you get a ketone on carbon number, let's say this is 1, 2, 3, 4, will you get it on 2 or 3? You can get it on either, okay? So if there is an imbalance of carbons on either side of the triple bond, then you will end up getting 2 products. Okay, so one will be like this, and then the other one would be where you had the ketone on the other carbon. So that happens. So you want to avoid having multiple products, so you choose an alkyne that is symmetrical, okay, unless you want those 2 different kinds of ketones. That's a different thing. So the important thing here is that if you were using hydroboration, you would still get a ketone because it's an internal alkyne. So you can use either of these 2 reagents. But if you have a terminal alkyne, then you want to be careful and choose your reagent carefully according to what product you have to make. Okay, so one will give you Markovnikov, one will give you anti-Markovnikov. Now, one last thing I want to mention before I move on from here, it's about the oxidation thing I was talking about before. So see here, the product is ketone. Okay, so I want you to compare a ketone with an alcohol. If you look at these two, ketone is more oxidized. Why is it more oxidized? Because it has less number of hydrogens on it, right? So when you had an alkene gave you an alcohol, but when you had an alkyne, that gave you a ketone. More oxidized alkyne gave you a more oxidized product. It's a very small thing to remember, but if you can, it's helpful. That way you will never make an alcohol from an alkyne, because you can see we're not making alcohols here at all. Hydration for us here means that you're getting a ketone or an aldehyde, okay? And that's because you're starting with an alkyne, which is a more oxidized, unsaturated system, okay? If you can remember it, okay. If not, that's okay. Just remember the reagent and the reactions, okay? That should do. Now for the reductions, okay? So we have a few reductions to talk about. So in this one, this is not the only slide. There's going to be, at least one more. So you can do a reduction of an alkyne all the way to an alkane, and you can do a reduction to go to alkene also, okay? So when you take any alkyne, whether it's terminal or internal, it doesn't matter, and you treat it with a hydrogen with platinum, palladium, as we've done before, then you can go all the way to an alkane. There is no stopping. There's no stopping in the middle, okay? So you go all the way to the alkane. So there's complete hydrogenation. So again, you have 2 moles of hydrogen here, okay? Not 1 mole, but 2 moles. I mean, if you want to write it, you can, but otherwise, it's excess of hydrogen. So you're adding it all the way through, okay? There is no stopping in the middle. But what if you do want to form an alkene from an alkyne? And you can do that, and that's in the next slide, okay? But if you're using hydrogenation, hydrogenation means that you're going all the way to alkane. So to form an alkene, of course, you'll have different reagents, okay, in there. So there are 2 kinds of alkenes that we can make. One is a cis alkene, and the other one is going to be a trans alkene, all right, in there. So there are 2 kinds of alkenes possible. Again, terminals will not give you cis or trans products. Remember that. It's only internal alkyne or internal alkenes that give you cis and trans, if at all possible. And we're talking cis and trans here because you are doing hydrogenation here, okay? All right, so if you wanted to do a syn hydrogenation, syn meaning on the same side, which means a cis product, to make a cis alkene, you have to do a syn addition. To do a syn addition, you need to use these reagents, which is hydrogen over Lindlar's catalyst. What is Lindlar's catalyst? It's given right here. So I didn't want to write it here. So palladium over calcium carbonate, and then you put hydrogen through it, and then that's your Lindlar's catalyst. Once you do this, then you end up getting a cis hydrogenation. This mechanism is very similar to what we talked about back in alkenes, where you have to provide a surface for the hydrogen to attach. Okay, that's an adsorption. So then the alkene comes and then picks up the hydrogen from the same side. Okay. If you do this once more, you'll get the alkane. Okay, but then of course you're losing the cis and trans, whatever. There's nothing cis and trans about an alkane. So what is the key thing about here? 2 things, okay, that are important over here. Number 1, you're doing a cis addition, okay, or a syn addition, and the other thing is you're using only 1 mole of hydrogen. If you were to do hydrogenation with palladium, then you would get 2 moles. You would get all the way to alkane. But if you're doing it with palladium and calcium carbonate, which is Lindlar's catalyst, then you get only 1 mole of hydrogen. Okay, so it's a very specific kind of a reagent that you can use to make alkene and to add only 1 mole of hydrogen. What if you wanted to make a trans alkene? So to make a trans alkene, you need to add the hydrogens on the opposite sides, which means anti-addition. To do anti-addition, look at this. Your reagents are completely different. Okay, so you're using either lithium or sodium. You're using an alcohol, which here in this case is C2H5OH, which is ethanol. So you're using ethanol. You could use methanol also if you want to. And then we are using ammonia, which ammonia is a base, so you can either use ammonia or you can use any other amine also, okay, any amine functional group. Amine functional group meaning NH2. So if you can, you also use CH3 NH2 if you want to, that's fine as well. But any of those combination of reagents is going to give you an anti-addition of hydrogen. The mechanism for this one is completely different from what we do for Lindlar's catalyst. Okay, this is a free radical mechanism which I have not covered over here, but it's a completely different mechanism, and that is how you can get anti-hydrogens, okay, on your alkyne, on your alkyne, sorry, okay, to give you a trans-alkene. So here you have two syntheses, okay, available to you to make different kinds of alkenes. Now there is one thing I just want to make sure you understand before I move on, okay, from here. So look at how I wrote these reagents out for you, okay. I wrote them in a very specific order, not because you have to write them in that order, because there is no 1, 2, 3 or anything like that, so you can add everything at the same time. But the thing about this reagent, okay, is that the main thing here is the sodium and the ammonia. This is just the solvent, okay, and sometimes if you don't write the solvent, at least I don't take off any credit for that, okay. So which means that you end up writing sodium and ammonia for me, but this is how you end up writing for me, and this is absolutely wrong because you have not given enough spacing in the middle and you haven't given any comma in the middle. So you have to write like this, because just now in alkynes, in synthesis of alkynes, we have learned sodium amide also, okay. So any NH3 by itself is not even a compound, okay. So you cannot write this and assume that you're writing this. They're not the same thing, okay. So be careful in how you're writing, because you know, it makes a difference. In chemistry, it makes a big difference, all right. And since we are so used to writing NaNH2, we write NaNH3 and we are done, and we are not done, okay, at that point. So be careful when you're writing all these reagents out. Your writing matters a lot to me. And then finally, we have the oxidative cleavage. Not finally, we still have more reactions to do, but on the alkyne itself. Okay, so oxidative cleavage here, whether you do ozonolysis or you treat with KMNO4, you kind of get the same products. Okay, so when you do ozonolysis or KMNO4, if you have internal alkyne, you will end up getting acids, okay, from it. Similarly, if you have a terminal alkyne, you will get an acid and then you will get carbon dioxide, okay. So because the alkyne, again, because it is more oxidized, you end up getting more oxidized products. And remember, with ozonolysis with alkenes, you got aldehydes and ketones. KMNO4 is a stronger oxidizing agent, so that's why it gave us carboxylic acids. But here it doesn't make a difference, okay. Here you're getting carboxylic acids no matter what, and if you have a terminal alkyne, then you're getting carbon dioxide, okay, regardless of whether you use ozonolysis or KMNO4. So that's oxidative cleavage for us, and I think, yeah, I don't think there's anything else I want to mention here. Right. Now for the acidity of alkynes, okay, so back when we did acids and bases, we talked about the acidity of all the three different kinds of hydrocarbons. So we have the alkane, alkene, alkyne, and you can see here alkane is not even an acid. pKa of 50 is like nothing, you know, I mean, like, it's not acidic. You can test the pH, whatever, doesn't matter. Even alkenes are not really considered to be an acid by any means. However, alkynes now are getting to a lower pKa value, okay? So they're not considered to be an acid like as a strong acid, but they still have an acidic proton, okay? So if they have an acidic proton, then you can actually pick up this proton and then return this into a conjugate base, all right, which is given right here to you. So what are we doing here? We have, first of all, this is a terminal alkyne property. Okay, this is not going to happen in internal alkyne. Internal alkynes don't even have a proton. Okay, so it's only going to happen in terminal alkynes. So in terminal alkyne, you have the hydrogen, and this proton is what's being picked up by the sodium amide. So again, we are dealing with sodium amide. That's a really strong base to pick up this proton. And then you get this kind of a conjugate base, which is called an alkynide ion. Okay. This alkynide ion is the conjugate base, and now what you've created is a base or a nucleophile. Okay, but this nucleophile is organic nucleophile in the sense that we're dealing with carbons. Okay, all the other nucleophiles we were dealing with was either OH minus, NH2 minus, we had the, iodide. So we had all of these kind of nucleophiles. We did have some methoxides also, which were organic. And these kind of organic nucleophiles give us different functional groups. Okay, so if you look back into the substitution reactions we've done, I gave you a list of reactions, okay, that we can do in order to form different functional groups. So here now we formed a conjugate base, and this conjugate base now can do other reactions also, okay, in there. So before I move on, there is one thing I want to mention here is about the base, okay, this one. The base that we need here to abstract this proton is going to be sodium amide. You cannot use hydroxide to abstract that proton. And I want you to think about why you cannot use hydroxide. Okay, if you use hydroxide, I cannot give you points because it's not going to work. Okay, so I want you to think about why hydroxide is not going to work. So write the reaction out. Okay, that let's say you have something like this CH3 here, this is H, and if you're using hydroxide, okay, what are you creating on the right hand side? Okay, think in those terms. I'm giving you a clue. So you're forming this, the alkynide ion, and then what else are you forming? You're forming H2O. Okay, so that is your reaction if you use hydroxide as your nucleophile. So if you use hydroxide, what's going to happen? Are you going to get as a result weaker acids and weaker bases? Okay, that's what I want you to think about. Okay, when you do this, when you're trying to figure out why hydroxide is not going to work. And the fact that I'm mentioning this to you tells you that I want you to think about it. Okay, because I can give you that question. And I also don't want you to use hydroxide. You might think, oh, it's an acidic proton, I can use hydroxide. No, you can't. Okay, you have to use sodium amide in order to do this reaction. Okay, so what happens when you have formed the alkynide ion? What can you do with it? All right, so once you form that conjugate base, there are things you can do because, now you have a wonderful nucleophile or, conjugate base, whatever. So here, this is a very nice reaction, which is called chain elongation. And the chain elongation is when you're treating this alkynide ion as a nucleophile. Okay, so if this is a nucleophile, then you can go ahead and do an SN2 reaction with it. Once you do that, what is happening? You're forming a carbon-carbon bond. Okay, so two things. I know everything has two things, right? So two things over here. Number one, you're dealing with a carbon anion first of all. Okay, this is the first time you've seen this species. We've dealt with carbocations, carbene. We've not done radicals. We're going to do that. That's our next thing to do. But carbon anion is your first negative carbon, okay, over here. And the second thing that I want to tell you is this very interesting bond, which is a carbon-carbon bond. Carbon-carbon bonds are very interesting in organic chemistry because here what you're trying to do is you're trying to form a carbon bond because one carbon has to be positive, the other one has to be negative, right? So it's a very different carbon that you're dealing with. A carbon-carbon bond, bonds form only when there is an electronic imbalance. And so here, because this carbon is negative and this carbon is not exactly positive, I mean, it's not a, carbocation, but it is still an electrophilic center. Okay, so now this carbon-carbon bond can be formed by just doing an SN2 reaction. Okay, so that's what this is. And depending on the kind of substrate you have, remember all the conditions we've talked about for SN2 reaction, that your substrate needs to be a primary halide, and those kind of things are all needed here, okay, for that kind of a reaction. So if you have two acidic protons, then you can do this reaction twice. So you can add different number of carbons on either side of the alkyne. So now you can get an alkyne of a chain length that you want. Okay, so it's a very nice way of synthesizing molecules, because once you learn how to form carbon-carbon bonds, now you can start building up your molecule. Okay, previously what we did, just made functional groups. One functional group converted to another. You made an alkene. Okay, now I'm going to make an alcohol. I have an alkyne. Okay, I'm going to make a ketone, right? So you're just interchanging functional groups. Now what you're doing is you're building up, it's a building block kind of a thing. Okay, so you can make long chain molecules or bigger molecules. You can also use alkynes as bases, okay, because they are a conjugate base of a weak acid. Okay, alkynes are not very strong acids. You saw the pKa was 25. So if you're using the conjugate base, which is a strong conjugate base, then you can use it as a base, okay, which means you can do elimination reactions. Okay, so again, this depends on what kind of a substrate do you have. So for example, here, if you look at this alkyl halide, you might think, oh, this is an alkyl halide. I can do a substitution reaction with this, but substitution is not going to work. This is sterically hindered. Okay, this is a tertiary halide. So even if you wanted to do an SN1 kind of a mechanism, that SN1 will be very hard too, because this is a bulky base. Okay, so everything makes it very hard. Will you get this at all via SN1 or SN2? SN2, forget it. It's not happening, right? Because this is a tertiary halide. But SN1 also, if you try, you probably will not get a whole lot of it. Okay, it will be a minor product. So SN2 definitely is not going to happen. So what you might end up getting is an E2, okay, which is an elimination reaction. So you end up forming a Hoffman product, okay, from this. So here also with the secondary halide, you can get elimination as well, okay. You can get substitution also. And if you want, I can add heat over here, and maybe I will add that in the PowerPoint, because as soon as you see the heat symbol, you're like, oh, okay, so now we are promoting elimination, okay, because generally, this kind of a ring, a 5-membered ring, is a flat ring, so there's not much steric hindrance going on here, okay. But because this is a strong nucleophile, and if I add the heat component to it, then you will get elimination here, okay. So which means that the SN2 or SN1 will be also very less, okay. And generally alkynes, you can do chain elongations, but those work very well with primary halides, okay, not so much with secondary. So I'm going to go ahead and add heat here, so it helps you to kind of internalize that you're going to get more of elimination reactions if you have tertiary or secondary halides, okay. All right, so solve problems. All right, so here we have first one, how will you make the ketone using an alkyne or an alkene? So from an alkyne, how would we make this? Alkyne, very simple, right? So this is a ketone. Ketone meaning I can start with this kind of an alkyne, and then, just use mercury sulfate. Now, you can also use an internal alkyne for this, right? So you can use this one also for it, but I wouldn't do that, because this one is only 4 carbons. But if it was 5 carbons, then we're going to have issues, okay? Because then you might end up getting 2 products, okay? So this is 1, 2, 3, 4, 5. So you will end up getting the ketone here, and you can also get the ketone here. Okay, so 2 and 3. So carbon 2 and 3 both are susceptible to forming the ketone, okay? So if you have a terminal alkyne and you are forming a ketone on the second carbon, just go ahead and use mercury sulfate. That's fine. For the other one, you're going to get 2 products, by the way, okay? In case there was a problem like that. Okay, and with an alkene, how do we do this? With an alkene, it's a much simpler, not much simpler, it's a longer route, but for an alkene, you cannot make a ketone directly from it. So what I've done is I have made an alkyne out of the alkene, which is by chlorination and then elimination. Once I have the alkyne, then I can get a ketone. There is no other way for you to do it right now. Generally, when you do all these kind of synthesis, you have to use the reagents we have learned until now. You cannot use any reagents from future, okay? Because yeah, there are so many more reagents, okay? But you use whatever information you have up to now, okay? Which for now, your ketone can either be obtained from alkyne or you can get a ketone from cleaving an alkene. So if you wanted to do that, you can do that too, okay? So for example, boop, boop, boop here, okay? See, if you have this kind of an alkene, and I'm just drawing it like this so that you can see that if you cleave this, then you will get this ketone, right? So you can use ozonolysis on this kind of an alkene. So you can either do this reaction or you can do this reaction. Both are fine, okay? So long it's an alkene and it's a reaction you have done before. All right, more. And then how will you make a trans hex 3-ene from but1-ine? Okay, so write the reaction first, okay? Don't go by the name, write the structures out so you can clearly see where the triple bond is, where the double bond is supposed to be. So 1, 2, 3, trans meaning that hydrogens are going on the opposite side, okay? So first of all, here I'm starting with but, so which means I have 1, 2, 3, 4 carbons, and here I have 6 carbons, which means the first thing I need to do is add 2 carbons to it. So if I'm adding 2 carbons, so then it means I need to do chain elongation over here. So carbon-carbon bond formation. So the first thing here, sodium amide, and then once I get my alkanide, then I'm going to go ahead and add the 2 carbons using an alkyl halide. Now once I have this, now 1, 2, 3, 4, 5, 6. I have 6 carbons now. And then on the third carbon now, between 3 and 4 is where my triple bond is, which is perfect because now I can go ahead and form my transalkene, which is sodium in ammonia in ethanol. Okay, comma, comma, comma. Don't forget the commas. All right, so that is a 3-step synthesis. I can give you longer synthesis. I can just give you this synthesis and not give you any reagents. Sorry, I crossed out the wrong thing there, and not give you any reagents and just ask you to fill the reagents, right? So you should be able to do that as well. So know your reagents, okay? All right. And then here, what are the products obtained from ozonolysis, which of course, again, it's just breaking bonds. And then in the question number B is how many carbon dioxide molecules am I going to get? And carboxylic acid functional groups will I get, okay, from the following molecule. Okay, so let's do the first one, which is the ozonolysis. And the ozonolysis means that I'm fragmenting everything. So if you look over here, what I've done is, of course, I've given you where I'm breaking the bonds. And then I kind of followed the same structure and just added the oxygens, double bonded oxygens. Okay, remember for ozonolysis, a triple bond is going to give us a carboxylic acid. Okay, so carboxylic acid here, carboxylic acid here. But if you have a double bond, then you're going to get an aldehyde or a ketone. Okay, that's what you're going to get. So here, since I don't have substitutions, more substitution on the alkene, I'm getting aldehydes. Okay, so aldehyde here and aldehyde here. Okay, then the B, KMNO4, how many carbon dioxide molecules am I going to get? So 1 carbon dioxide molecule, right? Because I have 1 terminal alkyne. So 1 terminal alkyne means 1 carbon dioxide. And then since we are dealing with KMNO4, let's see, this will definitely give us a carboxylic acid. Alkenes give us carboxylic acids, and then 1 carboxylic acid from this carbon. This, because it is more substituted, will give us only a ketone. Okay, it will not give us carboxylic acid. So 4 carbon dioxides Okay, excuse me, 1 carbon dioxide, 4 carboxylic acid functional groups. Okay, and then qualitative analysis. So qualitative analysis for alkynes is uh, it's the same as alkenes, which means bromination, and then you also have the potassium permanganate, okay, the decolorization of bromine and the brown precipitate. The only problem is that how do you then tell the difference between an alkene and an alkyne, right? So alkene is 1 degree of unsaturation, alkyne is 2 degree of unsaturation. So the only way you can tell from a qualitative analysis is by actually doing a little bit of a titration, okay? So which is not exactly a qual analysis, because qual analysis doesn't really involve anything with numbers or quantity, okay? But you can do a very crude qualitative analysis or a quantitative analysis by just using your pipette and, you know, your Pasteur pipette or something, and adding number of drops. But how would you know? You know, unless you have an alkene and alkyne to compare with, how would you know? So it's a little bit difficult to identify alkynes, so better to stick with spectroscopy for this one, unless you are told that you have 2 degrees of unsaturation or something like that. Something, there has to be some other clue, okay, in there for you to know. Okay, that's it, I guess, for us. It was a lot, wasn't it, in one? But some of it was repetition, so not too bad.